Today we will discuss rigid body motions in modern robotics. Page number 66 and 67. Here the case. Consider this rigid body with two reference frames fixed. This one is D and this one is C. D coincides with stationary frame, S frame, ground frame. This one is X, this one is here X. So this frame is at an angle of 180 with a stationary frame. Here we want to find the position of this point after rotation about origin 90 degree and then after displacing 45 degree. So we want to find the position of this point in S frame and orientation in S frame. This point goes here because of this, and then after it rotates like this. This one is reference frame D dash after rotating this. This one. This one is D. This one is our position vector of this reference frame. This one is P. We are rotating body by 90 degree this way. So R becomes here. So we have to multiply R by rotating vector P, which is angle 90. So P is cos 90 minus sin 90, sin 90 cos 90. R dash is what? So PR plus this vector is replaced here. So this is the final position of this point. R dash is PR plus P. It is nothing but triangle of a vector addition. So P is cos 90 minus sin 90, sin 90 cos 90, 0 minus 1, 1, 0. What about R? So this reference frame is at an angle of 180 degree. So R is cos 180 minus sin 180, sin 180 cos 180. So minus 1, 0, 0 minus 1. What about the final orientation of this point here? So for this we have to multiply P into R. P initially P, then after R, because of initially we are rotating body 90 degree and then after displacing. So P, initially P is here, 0 minus 1, 1, 0, minus 1, 0, 0 minus 1. So we have 0, 1, minus 1, 0. So PR is, we can say that cos of minus 90, 1 is minus sine of minus 90, sine of minus 90, cos of minus 90. So 0, 1, minus 1, 0. This frame is X, but this, if we rotate like this, so this is at an angle of minus 90 degree with respect to S frame. So orientation of C dash in S frame is minus 90 or plus 270. Do you know why we have taken R dash is PR, not RP? We will discuss later. Now for the position of C dash, this one. R dash is PR plus P. PR. P is this 0 minus 1, 1, 0. R is 3, 1 according to scale of this figure. 3, 1, this one, 3, 1. Plus 2, 2. If you multiply this, we get minus 1, 3 and 2, 2. So minus 1 plus 2, 1, 5. See, this is the origin of a stationary frame and this is the final position vector. This one is 1, this one is 5. So 1, 5 is final position of 3, 1. Initially the body rotates about S0, 0 by 90 degree counterclockwise. Then after it displaces by P, 2, 2. Initially rotate this way and then after it goes to at 45 degree here in S frame. We can achieve this final position and orientation just by rotation about a fixed point another way, S0, 2. Suppose this is new origin. We have shifted the origin 0, 0 to 0, 2. If we make welding to this body, here it is just welding, it is pivoted. So if we rotate this way, if you rotate this body this way at 90 degree angle, so this is the position vector R, this is the position vector of R, 3, 1. If we shift the origin at 0, 2, this one say, new origin say S, this is the vector 0, 2, S, S plus question mark equal to r, s plus question mark equal to, so question mark is what, r minus s. So r minus s, position vector of this r minus s in new reference frame, fixed point 0, 2. We are shifting the origin to s, h, k 0, 2. Now new coordinates of r in x dash s y dash frame. So r minus s, triangle law for vector addition. So 3, 1 minus 0, 2, which is equal to 3, minus 1. When it is rotated 90 degree counterclockwise, the coordinates becomes this one. This one is r minus s, r minus s. It is rotated by 90 degree angle. After welding here, this one is new vector, and then after we are rotating 90 degree, the coordinates becomes p into r minus s. We know that rotating vector 90, so 0, minus 1, 1, 0, 3, minus 1. So after multiplying 1, 3, say x dash y dash in x dash s y dash frame. Now we know that observe the figure, this one. X dash is x minus h. This one is origin. We have shifted origin to h, k. This point, according to old frame x, y, and new frame x dash y dash. This one is x, this one is x dash, this one is h. So x dash is x minus h, y dash is y minus k. After this, x dash is 1, so x minus h equal to 1, x minus 0 equal to 1, so x equal to 1. Y dash is 3, but what is y dash? Y minus k equal to 3. But k is 2 here, so y minus 2 is 3, y is 5. But how can we know around which point other than origin by 90 degree to achieve the same final position? So this is rule we have derived by example. So r dash equal to p into r minus s plus s. But we want r dash as 1, 5, and we want rotation 90. So this one rotating vector, r minus h s, we get this one, r minus s, 3, minus 1, this one. Sorry, 3, 1 minus h, k. So plus h, k. This is r, this is h, s. We want to find h, k. So 1, 5, 0, minus 1, 1, 0, 3 minus h, 1 minus k plus hk. 1, 5, after multiplication minus 1 plus k, 3 minus h plus hk. So 1, 5 minus 1 plus k plus h, 3 minus h plus k. Solving this, we get k equal to 2 and so h equal to 0. This way we can know around which point we have to rotate a rigid body to achieve same final position. Here we require same orientation also, so beta equal to 90. Now we are arising a question: can we achieve the same final position and orientation with rotation beta not equal to 90 with respect to s, h, k other than origin? Let's take beta 60, applying r dash equal to p into r minus s plus s. Obviously, we can't achieve the same orientation because of the body also rotates by 60 degree counterclockwise, but we want 90 degree still, 90 degree. Still we can achieve the same final position, not orientation. So 1, 5, p, suppose we want 60. So this one, rotating vector 3 minus h, 1 minus k, h plus hk. After this, we get two equations in two variable h and k, and they are having different slope. So we can solve uniquely. So we can get the initial final position at the same location, but not orientation. Do you know ax plus by plus c equal to 0? Slope is given by minus a by b. Suppose x1, y1, x2, y2. There are two equations satisfying this equation. Subtracting this, we get y2 minus y1 equal to x2 minus x1 minus a upon b, slope of the line. Okay.